In this video, we are going to see maxima and minima relating to a single variable function in calculus topic of mathematics, in which we use differentiation as basics. Maxima and minima are plural terms to maximum and minimum. If you are given a function f of x, say, and if it has maximum values and minimum values, so how do we find those maximum and minimum values? This is what we are going to do. For that, we will use the concept of differentiation in order to find these things. Okay? To start with, let us take a function f of x, which is a function of a single variable x here. Okay? And let us take an arbitrary graph for this f of x. Let us consider this f of x arbitrary waveform here corresponding to f of x with respect to a variable x. Okay? Now, looking at the basic definition of differentiation, if we take differentiation of f of x, say d by dx of f of x, at say suppose x equals to x1, what it means is, suppose let me take this point being x1, and if you take a tangential line which is touching this particular point in the curve, and if we draw a line here, okay, which is like tangential, okay, differentiation of this function at x equals to x1 is nothing but the slope of this tangential line drawn to this particular point. So the slope will be equal to the slope of this tangential line, or you can say this angle, say suppose here it is phi1, if we take tan of this phi1, the resultant value will be equal to the slope of the tangential line here. Okay, so that is nothing but the differentiation of this function at x equals to x1. So having said that, if you see in this particular region where the curve is increasing, okay, till this point, let's say in this particular region, if you look at this particular line, tangential line, where the slope is positive, okay, we have it positive. Suppose if you take a point, let's say here, and if you draw a tangential line again here, it will be something like this. Okay, suppose let's say this is line A, this is line B. Okay, slope of line B is positive still, but it has reduced, that's all. Okay, so if you look at this particular section over which x is changing, okay, where this f of x is increasing, in that region you have the slope of the tangential line as positive, which means you're going to have differentiation of that function over this region as positive. So we can say first, if we have slope, okay, slope or d by dx of f of x as positive, which means that the function f of x is increasing. Okay, it's increasing, and you can say that when it is increasing, if you measure the angles, this phi1 similarly as we measured here, this angle will be an acute angle. When we say this acute angle, this angle which we measure is the tangential line extending it so that it intersects this x-axis, and we measure the angle here. If this angle is less, it will be less than 90 degrees. Okay, I'm saying less than 90 degrees. It is called acute angle. Okay, so this is a conclusion on this. If a function is increasing, it will have its slope positive or differentiation positive value, and the angle it will make with the x-axis will be acute angle. So if you come to the second case where, you know, if you see this part of the curve, okay, here the curve is decreasing. If you look at the differentiation of, say, suppose at this point, okay, and if you look at the tangential line to that particular point and see here, okay, it is intersecting at this point, and if you look at this line and see the slope of it, the slope will be negative. Okay, let me make the point here. Okay, the slope will be negative. Okay, and when it is negative, if you can see, the f of x function is decreasing. Okay, the function is decreasing. And if you look at the phi angle measurement, okay, it's measured from in anti-clockwise direction from this x-axis. Okay, if you take the angle, this angle is actually obtuse angle, which means that angle is greater than 90 degrees. Okay, and the slope of this will be negative. Fine. So when you have the slope of the curve negative over a region, which means that the function is reducing in that region. Okay, so this is case number 2. Okay, now we have seen cases in this curve where the slope has been changing from positive to negative. If you look at it in a different way, okay, we are doing differentiation with respect to x in this direction. Okay, positive x direction, which means that you can assume this is like a hill where you need to you're moving in positive x direction, which way we are differentiating. Okay, so if you want to climb this, okay, it is in upper direction you have to climb, whereas this is negative slope where you have to just roll. Okay, it will be easy to get down. So this is how it is. So you have positive slope increasing, negative slope decreasing. Okay, now the slope has changed from positive to negative. There should be a point in between where the slope will be 0, right? So if you look at carefully here, there is a point, okay, where if you see to the right side the value is lesser than this point, and to the left side the value will be lesser compared to this point. So which means this point is the highest in that particular local region. If you see this local region, okay, this local region, that will be the point, the highest point in that local region. So at that point, if you take differentiation, or if you say take a tangential point at that tangential line at that point, you'll have a line, say it's D, and the previous one say C. Okay, so you have D line which is parallel to x-axis, which means that when there is a parallel line with respect to x-axis, the slope of that line is 0. Okay, which means the differentiation of that function at that particular point is 0. So if you write the third condition, okay, where slope or differentiation is 0, okay, then f of x is stationary. Okay, f of x is stationary. In this case, this is local maximum, okay, for that function. Fine. Now, okay, we will write this angle is also 0. Okay, now if you see the other case where we have like suppose if we look at this particular section of the curve, okay, the slope is negative from this region and it becomes positive here because the curve is increasing in value with respect to x. If you see a point here, we have a minimum point where if you take the slope of it, you will have a line, say E, which will be parallel to x-axis, where you will have the minimum value, local minimum of this function. Okay, so which means that it is stationary again there. Okay, so it can be a maximum point, okay, or a minimum point. Okay, that is a conclusion. So now our whole topic of interest is finding maxima and minima, which is nothing but plural of finding maximum points and minimum points, right? So we know a condition where if you are given a function f of x, you need to find the derivative of f of x, and we know that derivative of f of x will become 0 at points of x where the function is either maximum or minimum. So when you solve this particular equation, differentiation of f of x equals to 0, and this equation if you solve, you will get values of x, say x1, x2, etc., so on, say xn. Okay, these are all the x values over which the function can be maximum or minimum. There is no distinction yet we have talked about. We will see that in this video as we progress. Okay, so we know how to find the x values where the function can be maximum or minimum. Okay, so we know the values of x. Now let us move on to seeing how to find at a particular given x whether the function is maximum or minimum. Okay, in this figure it is very evident and obvious because we know the curve of it. In general, we will be given a equation of f of x, okay, and we will be asked to find out the maximum or minimum, okay, or local maximum, local minimum. Okay, fine. Now let us proceed with how to find a function is maximum or minimum at a given value. So now let me plot differentiation of f of x approximately in a graph here in order to understand the point where the maximums and minimums occur. Okay, I'm going to plot this differentiation of it. We know that from in this section, okay, towards the left, in this section we have this slope positive, okay, initially increasing. The rate of increase is decreasing as we go up. Okay, if you plot that section, okay, the slope is some positive value to start with, and it increases a little, okay, looking at the curve, and it drops down. Okay, this is an approximate curve I'm drawing. Okay, and we know that at this particular point where it is maximum, the differentiation is going to be 0. Now if we go here, the decrease, there is now negative value of difference slope. Now the slope negative magnitude will be increasing. Okay, and at this point, okay, if you see at the minimum point the slope will be 0. It's nothing but the differentiation becomes 0. So if we go like this, okay, oops, let me recall it. Okay, if you go like this, okay, it turns out to be, okay, like this. This is an approximate curve. Okay, so now if you see here, the slope is increasing, okay, from this point. So it starts, the slope also will start increasing, okay, till a point. Okay, oops, till a point. So this is how f dash x looks like. Okay, from this we can say that where it is 0, okay, differentiation, those are the x points for which the function can be maximum or minimum. Okay, now let us look at this f dash of x function and try doing f double dash x. When I meant f dash x is nothing but differentiation, okay, d by dx of f of x is nothing but f dash x. F double dash x, when I meant it's double differentiation of f of x function. So now let us plot for this f dash x differentiation downwards. Okay, now if you try drawing the differentiation of this function now, okay, initially it is increasing, okay, till this point. It becomes 0 at this point. Okay, I'm going to take this as a reference, okay, where it is becoming 0, and it will be negative till this point, where at this point it will become 0. Okay, so here the value should be 0, and it will be positive throughout. Okay, so now I'm going to start from this point where it is positive, okay, and it decreases to 0 at this point. Okay, and then it goes to negative value, fine, and the negative value decreases. Okay, it's actually the magnitude decreases and meets here at 0, and it will be positive afterwards. Okay, it will be approximately like this. Now looking at this, okay, let me summarize here. We are given f of x, okay, we will equate the differentiation of it to 0, so we will get these points 1 and 2. Okay, we know that the function will be either maximum or minimum at these 2 points, but we don't know exactly at which point the function will be maximum. Okay, now if you see here, the double differentiation of that function at this particular point will be negative. Okay, here if you see at that point it will be negative. So if we can summarize, okay, suppose we have df of x by dx equals to 0. We got x1 and x2. Suppose now if we take d square f of x by dx square, substitute x equals to x1, and if this value is negative, we can say the function is maximum at x1. Okay, we'll summarize it anyways. Okay, finally now if you look at the other one where we have the minimum value, we will get this particular x. Okay, let's say this is x2, at which double differentiation at that point for this function will be positive. So with that we can say, if we find this x2, if we do this d square f of x by dx at x equals to x2, we'll have positive. We can say this is minimum. Okay, this x2 is corresponding to this function's minimum value. Okay, so this is how we can say which point corresponds to maximum and which point corresponds to minimum, maximum and minimum. Okay, now if you look at this carefully, okay, there are some terms to define. If you see this curve, this section of the curve from top side, it looks like a convex shape. Okay, so we can call it as convexity. Okay, I'm writing it down here, convexity. Okay, if you look from top side, this portion of the curve looks like a concave from top side, so we can write it as concavity. Okay, concavity. Okay, and there will be a point, okay, in the middle of this convexity and concavity where the double differentiation of the function will become 0, which will be this point. Okay, that is called point of inflection. Okay, that point, if you extrapolate and find it out, okay, it will be somewhere here. Okay, you can call that point as point of inflection. Okay, let me write it down here. Okay, point of inflection. Okay, we have seen convexity, concavity, and point of inflection. The way to find point of inflections is double differentiation of the function should be equal to 0 and find the roots of that equation. You will get point of inflection. So having said all this and discussed all these concepts, let us summarize what we have seen and how to find out the minimum and maximum, or you can say minima and maxima of a function of a single variable, to be specific, and let's see how to find out point of inflection. Okay, now we will summarize on what we have discussed. Okay, you are given a function f of x in a polynomial form or whatever kind of. Okay, you are given a function f of x. Now if you want to find the maxima and minima of this function, the first step you need to do is find f dash x, which is nothing but differentiation of f of x, and equate it to 0. You'll have an equation. The equation is f dash x equals to 0, and find the roots of this equation. Okay, let's say you get the roots, and let's say they are x1, x2, etc., so on, xn. Okay, now you know that at these values of x, if you substitute them in f of x, you know that f of x can be a maximum value or minimum value. Okay, in order to find out which point corresponds to maximum and which point corresponds to minimum, what we do is, for a given x1, if you want to find is x1 corresponding to function's local minima or maximum, what you do is find f double dash x, okay, and substitute x equals to x1, and if it is equal to negative, it means x1 is corresponding to f of x maximum. Okay, to be specific, you should call it local maximum. Okay, and in order to find minimum, okay, if f dash x, if you substitute x equals to say x2, and in case if you get positive value of double differentiation, okay, then you can say for x2 f of x will have corresponding local minimum. Okay, so you may ask, if we have local maxima, multiple local maximas, what is the actual maximum value of the function? What you can do is, okay, there are some special cases also, okay, but in general we'll make a statement here, and when we discuss problems we will see that special cases also. Okay, so when you have multiple local minimas, what you do is you look at the value of f of x for all those x belonging to x maximas. Okay, multiple x maxima I. Okay, if you substitute each and every x value and find out f of x, and for which x the f of x is maximum, that is called global maxima. Okay, and similarly if you can do that for this all values of x for which it is minimum, if you compare f of x value for that, you will get a global minimum value of f of x and its corresponding x, of course. Okay, this is how you find maxima and minima of a particular function of single variable. And point of inflection, how do you find out, is you double differentiate f of x and equate it to 0. You'll have this equation and solve this equation and get the roots. Okay, and those roots at those points you'll have point of inflection. We have seen what that point of inflection is. It is nothing but changing of this convexity to concavity or concavity to convexity of a graph. Okay, thank you for watching.